last time I mostly got onto stating the results that are on the board. So just some review. So our setting, we're dealing with a number field. So this is finite algebraic extension of the rationals. And OK is going to denote ring of integers. And then we had some properties of polynomials that appear in statements. So the two main results are these sort of popular difference style results. First one, if we have jointly intersective independent polynomials, then for any measure preserving system, we don't even need ergodicity. We can get a synthetic set of popular differences. And we can also get, so this is sort of the extreme cases of families of polynomials. So here they're independent. Here we're looking at multiples of a single polynomial. You could also try considering intermediate things, but those would become sort of more cumbersome, more complicated. So I'm just sticking with these. In the second case where we have multiples of some fixed polynomial, we now do need to assume the system is ergodic, and we can get something for length 3 and length 4 polynomial progressions. And I've written here some remarks about this one. If you wanted to do something for, say, length 5, that will fail. And all of the assumptions here are, with the exception of this one, basically necessary, and some assumption about RNS is probably needed. So maybe not quite that strong of an assumption. So ergodicity, as I said, is necessary already at length 3 for some basically just version of Roth's theorem. You don't necessarily get U of A cubed if your system is non-ergodic. You can get some non-ergodic skew products that will have small intersections. And then for length 4, I mentioned these last time, but I don't think I wrote them down. There are some finitary combinatorial results that suggest that you need some restrictions on length 4 patterns in order to get large intersections. So some of these restrictions, I guess even, let's say these are all integers. Most likely you could cook a counterexample if they don't have this nice form where R plus S is this last one. So there's some finitary counterexamples from Sa, Sani, and Zhao. And then also the reason, well, actually, the reason for this assumption is really something dynamical about what we know how to do with structure theory, but probably some assumption is needed there. There's a recent paper also in some finitary setting that suggests that if you took R equal to 1 and S equal to I guess this is when we're sitting. So for this one, our number field is just we adjoin I, and so the ring of integers would be the Gaussian integers. And they have some finitary analog, basically, of this configuration being bad for large intersections. But it's finitary, it's not exactly this. So I can't say definitively that it doesn't work, but I'd be surprised if it does work. Okay, so I mentioned last time that the way, at least we take to prove these results, is establishing characteristic factors for some polynomial multiple ergodic averages. And then once we have those characteristic factors, we can play around it and get to this. So today, I'm going to start out by showing how to get from theorem C to theorem A and from D to B. And then I'll start at least making some reductions to move in the direction of proving theorems C and D. Probably won't finish that today. We'll prove some equidistribution results next time that establish those. Okay, so are there any questions on anything before I jump into some implications here. Let's see. I guess I'll start. So let's start by showing that theorem C implies theorem A. So theorem C just says if we have independent integer value polynomials, then the characteristic factor for the ergodic averages is the rational Kronecker factor. And really, more or less what I'm going to use here, well, I will use that, but maybe the most important case of this is if T is totally ergodic, then this average is going to converge to the product of integrals. The case, maybe unsurprisingly, that we're going to care about is when all of these fi's are equal to the indicator set of our function. And so then the right-hand side is just going to be like mu of a to the k plus 1. Maybe once we do another integration again. So let's start doing this, and I'm actually going to prove something a little bit stronger than theorem A. So what we're actually going to prove is the following thing. So if we have this same setup, jointly intersective, independent, and integer valued, for any measure preserving system, any set, and any positive epsilon, we can find some numbers. G is going to be non-zero, such that some average is large. This average will be mu of a to the k plus 1 minus epsilon.
Ethan,
Yeah.
hey, I'm so sorry to interrupt. So independence, is it like in the independence you're talking about in Z would be sense of Q independence?
Yeah, so
This
okay,
is
so it's a little bit different than linear independence, but actually because I'm assuming that the polynomials are jointly intersective, it will be the same. So it just means it's linearly independent over the number fields k. So these are polynomials with coefficients from k, and we're talking about independence over that field.
okay. Thanks.
Okay. Okay, so maybe before I prove this statement, let's see why this implies theorem A. So the first thing to realize, we're taking uniform Cesaro average. I'm not gonna prove, but it's a general fact that if you have some bound for a uniform Cesaro average, then the set of points where you achieve that bound has to be synthetic. Okay, so that tells you that at least inside of this set, C plus D times your ring of integers, you have a synthetic set of values where you achieve this, but if you're looking at multiples of D, that's going to be some finite index subgroup. And so the set of points that looks like this is also synthetic inside the full space. And if you're synthetic inside a synthetic set, you're synthetic inside the whole thing. You can just combine the finite sets that give you everything. Okay, so this is enough to establish theorem A, and it's actually stronger than A. So let's prove this. So we're going to start with the ergodic case. And then once we do the ergodic case, we'll do something with ergodic decomposition. So if it's ergodic, then we have theorem C ready to use. And what we're going to do is approximate the rational Kronecker factor by some particular finite rotation. So we can approximate the rational Kronecker factor by base of R, which I'm going to say it's all the functions that are invariant under multiples of R. So the rational Kronecker factor is just the inverse limit of all these things, so we can approximate it by one of these. I guess what's needed there is maybe some kind of nesting, but if R divides some S, then we get nesting in some direction. I'll write it down later. I don't want to mess up what direction it is. But okay, so we can approximate the rational Kronecker factor by this. And then what we're going to do is look at multiples of R. So the system here has finitely many ergodic components because multiples of R are finite in X subgroup. And so you know that the full group has to not have any invariant sets. So you can look at like different coset representatives. Those are going to just have to permute whatever is independent under this subaction, and there are only finitely many of those representatives, so you only have finitely many ergodic components. And I'm going to write these. So I guess, is this technically ergodic components? Maybe not. I'm going to look at the atoms of the invariant sigma algebra here and call them, say, x1 through xm, and these all have to have measures that are equal to each other, again, because they're just being permuted by different coset representatives. Okay, so I guess I can get rid of this. Okay, so now we're going to do, so maybe just so I actually can write down the real ergodic decomposition. Let me just define measures mu j by restricting the measure to xj. So again, these are all equal measures. This will be m times the measure of this intersection. And then the mu j, so the, I guess your ergodic decomposition is the average of the mu j's. Okay. So if we look at the power, if we look at this, we've essentially killed the rational Kronecker factor because this is going to trivialize the R invariant factor. And so now what we want to do is use the joint intersectivity to get all of these polynomials taking values in multiples of R. So because this is jointly intersective, we can actually do that. So this is going to imply that we have these values C and D such that Pi of this is contained in multiples of R. So intersective just meant we had, I guess, C, but then you'll actually get some D that works for this. If your polynomials, so if your polynomials all had integer coefficients, you can just take D equal to R. If they have denominators, you should take like something that will clear all the denominators times R, something like that. This is doable. And then we're going to let Q be polynomials. So Qi of x, make sure that's not correctly. Is going to be this polynomial, and by this claim, Ui is integer value. But now this expression is going to look like t to the r times qi, and so we can use some nice information about powers of r, or multiples of r. So by theorem C, let's look at this limit. So theorem C says that if we look at this limit, it's going to be controlled by the rational Kronecker factor. So this is the same as the limit, and I think I want to write the erotic decomposition now. Right, okay, so that's what I want to do first, actually. So before I do that, let me take the erotic decomposition. So just the same expression here. And now, what do I want to do? So each of these I can also rewrite. This is r times q1. And so then we get integral. Now we project to the rational Kronecker factor. And here I can write pi as r times qi. And I guess this is duj. And now we'll use the rational Kronecker factor is essentially just the r invariant factor. So this is, okay, here this is actually an approximation. So that's where the epsilon's coming from. And if we replace this rational Kronecker factor by case of r, well, we have a power of r here, so it will just be equal to itself. And so we really get this expression k plus 1 times. And okay, so the sum of the dvj's, so this is actually the same as just the integral d mu. And we can use Jensen's inequality to pull the k plus 1 outside. The integral of the conditional expectation of something is the same as the integral of the original thing. So this expression is at least mu of a to the k plus 1. Okay, and we lost an epsilon. Here, I didn't write it out all that carefully, but the epsilon is coming from how well you approximate the rational Kronecker factor. So that's the erotic piece. So this should look maybe similar to how you would prove Charpy using the rational totally erotic splitting. We took a convenient power of the transformation to trivialize the rational Kronecker factor. And then totally erotic systems, everything works out.
So how can you get from the third line from the bottom to the second line? Yes.
From here to here?
Yeah.
Yeah, so I'm using, I guess the question is, why is the rational Kronecker factor the same for the mu j's as the mu? Or so replacing the rational Kronecker factor with case of r is just
Right.
because it's an inverse limit, so we can do an approximation.
Right. That's true.
But also the if you're a rational eigenvalue, if you have a rational eigenfunction for some power of your transformation, it has to be a rational eigenfunction for the, or it's a sum of finitely many rational eigenfunctions for the original one.
Right.
So the rational factor for each mu j is the same as the one for mu.
Yeah.
So I was sort of hiding that away, but that is important.
Yeah. Okay. So, but then Yeah, so my question is like how can you replace all the yes.
Yeah, so this function, so I'm projecting onto the rational parameter factor.
Right.
I sort of skipped this. So first we replace the conditional expectation to rational parameter factor by the conditional expectation to this factor.
Right.
And that's where we lose an epsilon.
Okay.
But now if we're on this factor, we're just looking at the collection of functions that are invariant when you have multiples of R. And this has a multiple of R.
I see. Okay.
So it's an invariant function for this action.
Actually, how did we even reduce to just the ordinary Kronecker factor in the first place?
So we got to that's theorem C.
Oh.
So theorem C says if you have an ergodic system, then the average is controlled by rational parameter factor. And that's where we, so theorem C was right here.
Yeah. So this is very similar to first proof of Sarkozy. Yeah.
Yeah, yes. So for Sarkozy, you don't have to do, you can look at just the Hilbert splitting into rational until the ergodic. Everything works out until the ergodic. And on the rational spectrum, you take, you can approximate, you basically do this sort of approximation. You approximate the rational spectrum by a particular finite rotation. And well, if it's a finite rotation, you can kill it with some power of the transformation. And that's exactly what's happening here.
Okay, so this will show you the syntheticity of the popular recurrence, but it doesn't tell you like how big the gap between.
Right. I mean because basically, right. So D is okay. So it's some denominators times R, but it's a fixed multiple of R basically, depending on R. So if you have, all right, but then there's also so one thing is D, which depends on sort of how big of a finite rotation you need to approximate your rational Kronecker factor, but there's also a totally uncontrolled gap just from this limit. So yeah, I don't know. I don't think you can really get a lot of control over what the gap size looks like.
Yeah, I don't think they are either in integers case. We also don't know how big the
Yeah. But again, maybe next time I may, depending on time and what aspects Bill was most interested in, I can show that you can get something actually better than synthetic. So it still isn't going to tell you something about gap size, but it's a stronger, you have some stronger properties.
So do you use the R divided by S as rational in this?
No, so this one doesn't require it. There's no RS. It's just independent polynomials. So the next, I will also show theorem B applying D, and there I'll have to use something about rational, and I'll show you where it is.
Okay. One more question. That okay. So kind of you restrict to some kind of arithmetic progressions.
Yeah.
Right. But then in this I don't know, in this field, number field, this arithmetic progression is still like synthetic.
Yeah, so one of the properties that I'm using actually quite heavily in basically everything here, I haven't made it so explicit, but if you look at, okay, so if you look at multiples of D, that will produce a finite index subgroup. The index will be like the norm of D in the number field, something like that. So like if you had, let's just imagine if D was something like, I don't know, 1 plus I in the Gaussian integers, then that's going to have maybe index 4, because you take, is that right?
Yeah.
No, that's index 2.
Yeah.
Right.
The index
You take it's right. You take the So you do, if you have A plus BI, it's going to be A squared plus B squared as the index. Okay, so far I've actually only done the ergodic case. For the general case, we're going to use the ergodic decomposition, and that works out in this situation. So the important thing to notice in the proof here is that the choice of these values depended only on R. It had nothing to do with the dynamics. Well, okay, I mean, R had to do with it. How we chose R had to do with the dynamics, but once we have R, we can get these values. And so what we're going to do is now, so in general, we can write the measure as some basically convex combination of ergodic measures. And then for each of these, we'll let R omega be in the degree of integers so that the rational factor for that particular ergodic component is approximately R omega. Okay, and this approximation is going to have, I'm just going to write epsilon over 2 here. I haven't told you exactly what I mean by that, but we'll see how you're going to get a similar estimate like this, where you can replace the conditional expectation by this particular finite rotation, and when I do that replacement, I want my error to be epsilon over 2. Okay, so well, now what? So for any ergodic component, we have some finite rotation that will approximate the rational Kronecker factor. And now I'm going to let omega sub R be the set of ergodic components such that, is that the right direction? Yeah, such that R omega divides R. And this has to do with the nesting property that I alluded to. So if R divides S, then you have this inclusion. So if R omega divides R, then then case of R will also be an even better approximation. And then we can just choose some R such that this is basically the whole space. So right, so we have some inclusions. So we have this measure rho omega R, as R increases, is going to eventually be the whole space. And so we can use continuity of the measure rho to get omega R to basically be everything. And here we'll get the other epsilon over 2. So all that's happening here is just to formalize the statement that we can get basically a uniform finite rotational system that will control all of the rational Kronecker factors for every ergodic component. And that's why things work out. So as I said, C and D only depended on R and not the dynamics. So for every omega now in omega R, we can get the expression with mu omega to be at least this big, the epsilon 2 coming from this epsilon over 2, and then we'll get another epsilon over 2 from this part when we apply Yancey's inequality. So maybe let me skip some of the inequalities, but then we just integrate over omega, and we'll do one more application of Jensen's inequality, and that will get you this inequality. So you just write this as the integral of the mu omega expressions. On omega R, you can replace it by this. Outside, you only have an error of epsilon over 2. And so you have 2 epsilon over 2s that add up, and then you can apply Jensen here, pull the k plus 1 outside, and you'll get the value. Okay, so that's the end of the proof of theorem A, assuming that we have some knowledge about the characteristic factors.
So you cannot play this game in the other case, right?
Right. So in the other case, the factors that are controlling it, Yeah, I mean, I don't know right, the thing that's convenient here is the rational product factor is an inverse limit of some finite factors, and they have nice inclusions, and so we can get some kind of uniformity or almost uniformity, right? We can get to throw out part of the space, but basically we can get some uniformity in the characteristic factors on all the ergodic components. And if you are in the case where, say, the full Kronecker factor or some extension of it is controlling your averages, you start losing this behavior. So maybe that's some way of seeing it. I mean, there are explicit counterexamples for non-ergodic system for the other theorem. Okay, so now I want to show theorem D implying theorem B. I might skip some details, but I'll at least give you the general idea, and I'll cheat a little bit to just save time. So I'll say something that's like not really quite true, but is morally the reason behind what's happening. So now I want to show D implies B. So I erased both of those theorems. So D is a statement that if you're looking at multiples of a fixed polynomial, then the characteristic factor is the nil factor of the same step size you would expect for linear averages. And then B is the large intersections result for when we have multiples of a fixed polynomial. Okay, so yeah, let me do it not in a ton of detail. So we want to show it for ergodic systems. First, I'm going to do something for totally ergodic systems, and then we'll use intersectivity to basically reduce to the totally ergodic case. So we'll assume P is totally ergodic. And I don't think I actually wrote it today. Last time when I wrote theorem D, what this says is that, maybe in particular, the limit of this expression how do I want to write this? Maybe let me write it with this sort of general form. So if we look at multiples of some of our polynomial, this is the same as the linear average. So not only is the underlying characteristic of the factor the same, but the average itself is the same. Sorry, I'm going to replace P by just N. So that's what total ergodicity gives you. And okay, this doesn't quite say that syntacticity of large intersections is equivalent. It basically says that there are some details to make it work, but I'm going to pretend that's what it says just to make things a little easier. So if it's totally ergodic, essentially polynomial behavior is the same as linear behavior. And then it's just a question of what do we know for linear averages. So in the linear case, we know that any pattern of length 3 is going to work out. And we know that any pattern of length 4 will work out if all of these L's were integers and like genuine integers, not from the ring of integers. And you have some parallelogram configuration. At least that's all we know how to do from the joint work with Dr. Bergelson and with Andrew, and independently, or Shalom has the same results again, where we have to restrict to genuine integers, not a ring of integers. And so the condition that the ratio of S and R is rational is saying that R and S are lying. So let me just draw a picture. This is, I'm not going to write down too many details here. So let's just look at like the Gaussian integers. So we know that we get good behavior if, say, we had, you know, points here, here, and then there's some which is maybe like here, whatever. We can actually say, so right, so here's like the integers and here's I times the integers. So if S over R is rational, that's saying that all of our points lie on some line, maybe here, and we can just replace, instead of looking, so if we had Rn and Sn, we could instead look at, again, by this kind of property that the averages don't depend on what polynomial you choose, you could replace it by R times some an and S times some an, but then you want maybe say AR and AS to both be on this axis. So you can rotate this whole line to the axis by some A, and then the averages are going to look the same. So the S over R condition is basically that they're both sitting on this axis. So it's just, if you could prove, so the real obstacle is just some limit on what we know how to say for linear averages. And you know, obviously, if something's not true for linear averages, it's not going to be true for polynomial. Okay, so this was very hand wavy, but gives some sense of the totally ergodic case. And then why can we get from the totally ergodic case to the ergodic case? That's where we need our polynomials to be, or our polynomial P to be intersected. So here we didn't even care if P was intersected. If it's totally ergodic, it doesn't matter. Because the reason for the intersective condition is some issues with finite rotations. If you have a totally ergodic system, there are no finite rotational systems sitting inside. So intersectivity doesn't even matter. Okay, so what do we do in the regular ergodic case? So we still know that this average is controlled by the k-1 step nil system, and or nil factor, and so we can approximate that by, right, nil factor is an inverse limit of nil systems. We can approximate it by an actual nil system. So we'll approximate the k-1 by a nil system. Okay, and the convenient thing is if we have a nil system, its Kronecker factor has to be an abelian group, which has to have this very specific form. So the Kronecker factor, when we've done this approximation, is going to look like some number of finite rotational pieces and some number of tori. So once we've reduced to a nil system, basically our rational Kronecker factor is actually just a finite rotation. And so now we're just going to kill this finite rotation and use intersectivity to get to something totally ergodic. So this means that there's some k.
Wait, isn't the Kronecker? I was gonna say the Kronecker is always a finite rotation, but you could take an inverse limit of finite rotation.
Right.
So I was
Exactly.
mistaken.
Yeah, so we're doing, this is actually what we're doing by approximating by nil system is very similar to what we did on the last proof where we approximated rational by finite rotation. We're just doing a slightly different thing, but it includes that. Okay, so then there's some k that will kill this entire rotation, which means that, in other words, when we look at this action, this so that will have finitely many ergodic components, such that each of the finitely many ergodic components along this power, so each of them is in fact totally ergodic, because this disappears. So the Kronecker factor is going to look like tori, and it's a fact that if you have, well, okay, I mean, basically, this is the rational power factor. You killed it. You can also say that if you have a nil system on a connected space, it has to be totally ergodic.
So
Ergodic.
yes, so KDA can be taken to be the number connected component of your new system.
The rational Kronecker, yeah.
No, I mean, actually, if you want like C to the K, and so you say totally ergodic on the entire system.
Yeah.
Okay.
And so, I mean, the point is, if you're totally ergodic on the Kronecker factor, you're totally ergodic on the whole system. Because any failure, the Kronecker factor contains the rational Kronecker factor, and any failure of total ergodicity is captured by the rational Kronecker.
Yeah.
So another way of thinking is maybe is if you look at, so you can look at the splitting to Kronecker and weak mixing. On the weak mixing part, this multiplication by k gives you a finite index subgroup. And if you act by finite index subgroup on the weakly mixing part, it's going to remain weakly mixing.
Yeah, I see. But then, okay, so but then this one, after you do all the like approximations, right? Because like in a general system, like a general ergodic system, there may be no case of that when you speed it up, like not speed up, you like TKN will be totally ergodic.
Right. So that was because we did this approximation. So the way you can think about, maybe another way of thinking about this is basically the same thing we did in the last group. Just look at the rational Kronecker factor of your system, and then approximate by a finite rotation. So if the rational Kronecker factor is a finite rotation,
yeah,
then you have this property, because you can take a power that will trivialize the entire finite rotation. And so you have to know, you've gotten rid of the rational Kronecker factor, which means at least on ergodic components, it's totally ergodic.
Yeah, I see. So yeah, that makes sense. This makes sense. Yeah. So the way I think about this, so you approximate your neo factor by some neo system.
Yeah.
Then in the neo system, this is the concrete neo system, so it has to be
So yeah, another way
connected component.
Yeah. So another way you can think about this is exactly for a nil system. Nil systems have this property that you can find some power that will be totally ergodic on ergodic.
Yeah.
Because abelian groups can't have too much
Yes.
finite rotational stuff.
Absolutely, yeah. So neo system, neo manifold in general, it's just to be finitely many connected component.
Exactly.
And if you do the
And each connected component is totally ergodic.
totally, yes. So
Yeah. So this is also, you can think about this exactly. It's indexing the connected components, and the group structure here is just telling you how the different connected components get permuted by different pieces.
right.
Okay, so now once we have this k, that's why we need our polynomials to be intersective. So we'll do the same thing from before. So p being intersective means that we can find p and d such that this polynomial is integer valued. And okay, so what's the point? So now if we look at so if we look at t to the k times something, at least on ergodic components, that's totally ergodic. And we know that things work out in totally ergodic. So that's going to tell us that if we look at t to the k evaluated along q, things work out. Or in other words, so I'm going to write this sort of vaguely, but we have a syntacticity for this expression because t to the k, we have total ergodicity, and q is still some, well, it doesn't matter. It's an integer value. Okay, what does this mean? This means that we have syntacticity for p, because k times q is just p evaluated on some specific place. This is syntacticity for p, say within this set. And by the same argument as before, this is a coset of a finite index subgroup, so it's synthetic. If you're relatively synthetic in a synthetic set, then you're synthetic in the whole space. So this implies, in fact, syntacticity for p. And then that's the end of it. Okay, so there were some technical details I skipped over. So there's some technical details to actually make this argument extend to saying that the large intersections results are the same. And then there's also something I skipped over a little bit here is there are finite linear ergodic components here, and you need to make sure that there's some compatibility between those ergodic components. Because really we only have this claim on each ergodic component separately, but you can show that they're compatible in some way. And so you can average over all of them and still get a positive result.
So it still remains to prove the that's what the linear, the intersections along the linear iteration is good.
Sorry, what can you repeat it?
I mean, so you prove that okay, so it still remains to prove the.
Isn't that just a consequence?
Oh yeah,
of
so the linear case I'm just using as a black box.
Okay.
My results with Andrew and with Dr. Bergelson.
Okay.
So the linear case is a special case of what we show there.
Oh, I see.
Wait,
And so this is really, I mean, if you want to know why what we proved here didn't appear previously, I think a big part of it is that the linear case was unknown until, or some of these linear results were unknown until recently. So, do you have a question?
I was just confusing it with so Furstenberg's Szemerédi theorem for abelian groups or multiple recurrence theorem for abelian groups was just a lower density. But you're doing a uniform Cesaro limit.
Well, so that's not really the issue. So the if you just want to show that this limit is positive, that's a very old result. Well, maybe we need to be careful, depending on how safe. If you just want to show this is positive, where all of the LIs are genuine integers sitting on this axis, then that's well known for a while. What is recent is getting a better bound on this average. So not showing that it's positive, but that it's as good as possible. I'm actually cheating a little bit. These averages can actually still be small. But if you do some twist on this average, you can get it to be big. And that's why there's some details that are slightly missing. But basically what I've shown here is that if you have a linear result, or at least the philosophy here, I haven't fully shown it. If you have a linear result, you can improve it to a polynomial result. And then I'm using as a black box some linear knowledge. Oh, I just saw there's some stuff in the chat. Oh, okay. Okay, what do I want to do? So yeah, so what remains to do is show theorem C and D on characteristic factors, which is going to be some equidistribution. Basically out of time. I don't know. So I could start doing some reductions for the equidistribution results. Or I could end here. I don't know what.
I mean, do you think your part 3 is overly packed? So that it would really help.
Maybe, I think it would help to do some reductions now, but I also don't, if you wanted to get somewhere else, I could also end.
I mean, I think I don't know, I can spare 5 minutes.
Okay,
So I thought
sure.
Zoom people can also do
They have no work.
it. Oh, yeah.
Well, it's also recorded, so if they
Oh,
can,
sure.
potentially. Okay, so.
Balashash, what's going on? I think we're just gonna go up to 5 minutes over time.
Oh, 5 minutes is fine. Yeah, I have office hour at 2 though, so I will leave at 1:50. Please don't mind.
Okay. I'm just gonna clear the board, so I have space.
Oh, Ethan, while you are clearing the board, may I ask a potentially stupid question if you have already not mentioned it?
Go for it.
So all the work, how much? So in this, like, how much is the machinery of number field actually important? Can one do this in slightly more generality?
Slightly more generality, yes, much more general than you know. So the important features of reasonable integers. So one that I've at least hinted at quite a bit today is that if you start looking at some set of multiples that has finite index in the full ring. So that's one property that's used. And the other thing that I'm using quite heavily is that the group structure of the ring is like ZD.
I see. So
I'm using that in order to say that the characteristic factors have the structure of nil systems.
I see. Because I was going to wonder that the reason we took finite index is mostly for total ergodicity, right?
It's used in a lot of different places in slightly different ways. So
I think I noticed like 2. Can you?
Yeah. So right. So for total ergodicity to make sense. So my definition of I didn't actually write down what I meant by total ergodicity. What I mean is restricting to any set of multiples, you still have ergodicity. So it is hiding there. It's also important for basically any of the structure theory to even start working. You need this property because say you didn't have that property, then when you start going to powers or some set of multiples, weakly mixing systems may stop being weakly mixing.
That is actually very good way.
So that's part of it. And the other thing where it's used is I've today also had some situations where my system, I took an ergodic decomposition, and it was really important that it had finitely many ergodic components. So I didn't show enough detail to really see why that's so important, but it actually is quite important that the ergodic decomposition has finitely many ergodic components. And again, that's because of finite.
You did mention
it's used in a lot of different ways that are all kind of related, but it's very important.
Oh, I see. So like presence of infinite index subgroups can really be a problem. I see. Thank you.
Yeah. So there's a result. Here, write this. So there's a result that you can find an ergodic system, an ergodic Z2 system. So T and S are commuting, and you can get an expression like this to be bounded by mu of h to the fourth. So this is like looking in Z2 where our subgroups are the coordinate axes. And so there now we've got some infinite index and we lost the ability to get mu of a cubed. So that's just one example, but everything sort of breaks down.
Thank you for explaining it so patiently also. Thank you.
Okay, so let me start doing some reductions for equidistribution. Okay, so the first thing, I stated this last time, maybe I'm just gonna put it not in full technical language, but there's a result that characteristic factors or polynomial multiple organic averages are nil factors. So this is the results I wrote down last time from Bergelson and Robertson. If you have some collection of essentially distinct non-constant polynomials, and you look at the organic average, so the uniform Cesaro limit, then there's some nil factor that controls the average. Doesn't give you really any information, or at least nothing straightforward for what the step of that nil factor is, but there's some nil factor. And so what this means is that we can just assume that whatever system we start with is itself a nil system. And just to review, what does this mean? It means that X is a quotient of a nilpotent Lie group by a co-compact discrete subgroup. And then T, so B is then Borel sets, mu is the Haar measure projected down to this group, and T, to the NX is this, where A is some homomorphism from the ring of integers to your group G. So it acts on your space by just some translations. Okay, and then what we're going to do is just reduce. So this result tells you that you can assume it's a nil system, and then we can use some other sort of black boxes about equidistribution to reduce this to an even more convenient system where we can start to do some calculations and say something. So maybe next time I'll talk about this other reduction. Let me start with a reduction to tori. So this is related to some equidistribution results I talked about, I think, in the spring. So we can look at the abelianization of our space here. So I'll let G0 be the connected component of the group, of the identity in G. And then we can look at the space Z, which is X modded out by the commutator subgroup here. So this is the abelianization. And we have a projection from X. Right, so by modding out by commutators, we get something abelian, and there is a result due to Leibman. This is 2005. That allows us to reduce to studying things in the abelian part. And this you should maybe think of as like a very general version of Weil's criterion. So if X is a connected nil manifold and G, okay, X is some point, and G is some polynomial sequence. Let me not define that right now, but just think of taking something like this and evaluating not at n, but at a polynomial of n. And okay, so if you have a polynomial sequence in a connected nil manifold, then you have a bunch of equivalent statements. Let me write it in sort of the strongest way. So say you want to show that this polynomial sequence is, okay, what's the strongest thing we might want to say? We want to say it's well distributed. So that means like uniform distribution, except we get the statement of uniform distribution averaging along any polar sequence. Or equivalent, you can say that evaluating the uniform Cesaro average of a continuous function along the orbit will get you to the integral of the function. And what's sort of the weakest? So this is an incredibly strong statement. What's a weaker statement? We look at the projection of this sequence onto the abelian part, and all we have to show is say that this is it. Okay, so this, you can, as I said, sort of think of like a generalized version of Weil's criterion. So Weil's criterion would say, if you want to prove Weil distribution of some sequence in or some polynomial sequence like this in a torus, then all you have to do is check that none of the characters vanish on the orbit. And this being dense, there's some version of characters for nil systems. This being dense is actually the same as saying that you don't have characters vanishing on the orbit. But I'm going to leave it like this, and so what this allows us to do is, instead of looking at a nil system, we can look at just skew product systems on tori and prove some density orbits. I'm actually going to prove maybe Weil distribution via Weil's theorem and polynomial distribution or something, but basically we're going to show this, and being able to deal with the abelian systems is much easier because they have something more concrete to work with. So yeah, so I'll end here for today, and then next time we'll pick up and prove some equidistribution theorems for systems on related to tori, and if there's time, maybe I can make some other additional comments.
Why is Z called the abelianization?
So we've taken all these commutators.
Yeah.
So think about
Oh, so now any
all the
polynomial
commutators are
is zero
trivialized.
commute.
Yeah.
But I guess I'm just confused because X is not a group. X
Right.
is a set of
So yeah, so let's see if I'm gonna screw this up if I try writing it down probably. You can write this as, I think this is the same as something like G I probably screwed that up slightly, but it's something like that. There's an isomorphism between this and something at least similar to what I wrote here. And now you have abelian modulo some Koch-Mechanism. So I think I wrote this slightly incorrectly, but if you look at Leighton's paper, it's definitely written correctly there.